All right, good morning. Here we are yet again for another lovely session of MENG 3310 Fluid Mechanics. So today we're going to continue with the 34th video of the series, and this will be our last day on flow rate, on Darcy-Weishbach equation, on the Moody diagram, and all of these related subjects. And then we'll have one final topic, which will wrap up the course, and we'll work on that tomorrow, or work on that on Wednesday and Friday, and that will be a brief introduction to drag and lift. But my lesson objectives for today are I wish to cover the topic of using iteration to solve for V, D, and Q. So let us discuss this. Iteration to find V, Q, and D. So sometimes we don't know, in all of our previous examples, I've either given you the velocity or I've given you the flow rate. I've given you one of these things and it kind of just fixes everything in place. But in certain cases, we don't know either of those and we actually have to kind of iterate or go through a recursive process in order to solve for these. So let us consider a pipe like this here. So consider a pipe, this is going to be 2 inches in diameter and it's going to be made of drawn copper tubing. So this is going to be, again, drawn tubing made of copper. So drawn tubing, like you might see in some old style plumbing, or you might see in, various applications. I'm reminded of something like a refrigerator or an HVAC system or something like that, or a condenser coil, or that kind of thing. But anyway, let us say here that the pressure 1, P1, so this is going to be point 1 and point 2, so we're looking at a length of pipe. And let's say here the pressure 1 is 100 psi, and which of course is equal to 14,400 pounds per square foot, just multiplying by 12 squared pressure, pounds per square foot. And this is quite a long length of copper tubing, but that's also why it's going to have a fairly decent length, fairly decent diameter. So this thing is going to be 1,000 feet long. 1,000 feet long here. Let's see. Actually, let's make that, let me think here. Yeah. Sorry, let's make this, 1,000 feet long. Can decide whether I want to do 1,000 or 1,100. So let's say 1,000 feet long. Then, let us say again that this is 2 inches in diameter.
Is it 1,000 or 100?
1,000. What's the power of 10 among friends? And this will be 2 inches in diameter. And we're told that there is some flow rate flowing through this thing of Q, which makes sense. There's some flow rate Q, and that it's also full of water, H2O, aqua, agua. Pick your name, it's all the same stuff. One of those things. Or also, as it's commonly referred to, dihydrogen monoxide by some odd people. So the first step will be to look at the energy equation. And so we want to analyze this essentially. Now, let us look at the energy equation. So let's start by looking at the energy equation. And by doing this, we can see our issue. So we'll look at the energy equation. And if I consider this, I can say I have P1 over gamma plus over gamma water perhaps, plus V1 squared over 2G plus C1 is equal to P2 over gamma water plus V2 squared over 2G plus Z2 plus FLV squared divided by 2GD. 2GD. And then canceling out equivalent terms. Well, let's see here. Well, and let's say also this is emptying into the atmosphere. This is just a free surface here. It's just emptying the pipe out of the pipe here. So I know then that P2 is going to be equal to 0. So that term goes to 0. The velocities are not 0, but they'll cancel out because there's a constant flow rate, and because there's a constant diameter pipe, there must be a constant flow rate, and thus there's going to be a constant velocity via continuity. And then it's a horizontal pipe, so the elevation here. So we have the elevation here, and then go away, Autodesk, and this can then collapse to that P1 is equal to FLV squared, FLV squared times, and let's say I can actually solve this. So if I want to get rid of the G, I can say times rho water divided by 2D. So I now have really several independent variables. I have the pressure, I have the friction factor, I have the length, I have the velocity, the density, and the diameter. Now, let's look at this in terms of what I have and what I don't have. Now, I have this, I have the pressure, I have the length, I don't have the velocity, I have I have the density, and I do have the diameter. However, do you see the issue here? I have too many unknowns. I have three different unknowns here: the friction factor, the velocity, and well, I guess the friction factor and the velocity are my two unknowns. Sorry. Here I have two different unknowns, and the problem with this is that previously we've been using Reynolds number, and we need to know one of those to really solve for that. So, again, problem. How do I find Reynolds number? How do I find the Reynolds number without V? Usually we need the Reynolds number to find the velocity. And so how do you find, or I need the velocity to find the Reynolds number. And how do I find F without Reynolds number? How do I find the friction factor without the Reynolds number? This may be turbulent, and if it is, well, then we're going to need to use the Moody diagram, and then we need to know the Reynolds number, and quickly we're going to end up going in circles here. This is the issue. See, the issue with the Moody diagram is that it's a useful tool, but it is a diagram, in the sense that it's not a very simple input-output function. It's a chart. It's a tool. It's not like if I were to borrow a term from, say, grade school algebra, I would use the term, this is not a function that passes the vertical line test. If you remember way back in your high school math class, remember the actual definition of a function. Do you want to review through that again? That'd be so much fun, but let's not. But anyway, so it's not a function in the sense that there's not one clear output for one clear input. You need multiple inputs and you get one output from that. So that's the issue. So again, when solving for V, Q, or D, for V, Q, or D, cannot directly use the Moody equation. Use Moody diagram directly. So we need to solve iteratively. And we'll see what that means in this context. Now, I'm sure you've heard the word iteration before. That's not something new to you. But in terms of this context, it may be a bit odd, which is why we're going over it today. Okay. So the first step will be to start with what we have. Let us start with what we have. And, well, what do we have? We have the relationship P1 over gamma is equal to FLV squared over 2GD. Over 2GD. Now, I'm going to solve for things in terms of what I don't know. And so because I don't know the v or the f, I'm going to solve for v. I'm going to solve for v in terms of f. Basically, I'm trying to put this in a form that will allow me to easily integrate. Or sorry, easily iterate. And then I want to collapse this down to a very simple equation that I can then quickly use again and again as I iterate. Solve for v in terms of f. In terms of f. So I want to know a very easy expression for the velocity in terms of the friction factor. And let's do that then. So if I take this and solve it in terms of v, I can get that v squared is equal to 2gd times p1 divided by gamma fl, and this is 2 times 32.2 feet per second squared times the diameter of 0.167 feet. That's just 2 inches converted to feet, times 14,400 pounds per square foot, divided by a gamma of, well, our standard gamma of water for English units, of course, is 62.4 pounds per cubic foot, times our unknown friction factor F, and then times, actually, let me write this over here, times 1,000 feet times our friction factor F. And this then comes to 2.48 over F. So again, I have a very simple expression now that I can use in my iterations. I don't want to have to do this every single time I iterate, so I'm going to collapse a lot of these expressions down to something that's very easy to plug into my calculator again and again and again. So again, I could make the square root of f, but it's just as easy just to use the v squared. Now, my next step, I want to solve for my Reynolds number in terms of my velocity v, using the same idea, and that's not 2 times 48, that's 2.48, in case that's not clear. So velocity squared will be equal to 2.48 divided by f. Next, I want to solve for the Reynolds number in terms of velocity. Solve the Reynolds number in terms of velocity. And this is going to be Reynolds number is equal to Vd divided by mu, or sorry, not mu, nu. Vd divided by nu, so it's the velocity times the diameter divided again by the kinematic viscosity. And so that's v times 0.167 feet divided by the kinematic viscosity of water, which will be 1.21 times 10 to the negative 5 feet squared per second. And I then, from this, can get an expression that says the Reynolds number is equal to 13,774 times v. 13,774 times v. All right, so let's continue. Then another thing I'll need to use in referencing the Moody diagram is the relative roughness. And this is going to be, well, let's say because it's drawn copper tubing, a term I can look up is the epsilon for that. And the epsilon is going to be, okay, hang with me here, we're going to have a lot of zeros, 0.0000005 feet. So it's a very small amount. It's copper tubing, drawn copper tubing is fairly smooth. So 0.000, so 5 zeros after the decimal place, 5 feet. And this means our epsilon divided by our d is going to be 0.00005 feet. oh, and it's 0 point that, divided by a diameter of 0.167 feet. Again, as we work through these, as we've seen before, the devil with this is always the units. And so this then comes to a relative roughness of 0.00003. Isn't that lovely? Many zeros today. So we'll need to use these. And maybe we'll go ahead and put a box around this one too, because we'll be using this a lot as well. Oh, derp if I can manage to write a box properly. Okay. So, basically, we are going to use these three to solve iteratively. So these three equations that I've developed, so big idea, use these three to solve iteratively. Use these three to solve the problem iteratively. All right, now, so the first step, I'm going to assume a friction factor. And I'm going to start by assuming something near the middle of the Moody range. So assume, I'm just going to go ahead and assume that F is equal to 0.02. And again, this is, I did this because this is in the middle of the Moody range. And then I'm just going to go through and find if I assume one of those things, then I can just go and calculate everything else that would come out of that if that were the case. So the first thing I'm going to do is get the velocity. Then I'm going to get the Reynolds number from that. Then I'm going to get, well, the epsilon over d, that's not going to change. And then from this, I'm going to take the results from here, here, and here, and I'm going to put this in Moody, F from Moody, and that will be my next stage of iteration. F from Moody. So the first thing I do is I can get the velocity, that if this thing were actually true, if the friction factor actually were 0.02, the velocity would be equal to the square root of 2.48 divided by 0.02, and this would mean the velocity would be 11.14 feet per second. Again, this is not necessarily the actual velocity in the system. This is just what it would be if the friction factor were 0.02. Then the Reynolds number, again using the equation I developed previously, is equal to 13,000. And so now you can see why we developed those collapsed forms of the equations, just to allow for very quick iteration, times 11.14 feet per second. And this would produce a Reynolds number of 1.53 times 10 to the 5th, which is indeed greater than 4,000. So this would be turbulent, as we've kind of assumed in our initial analysis. And the epsilon over d then is going to be and that's not going to change. The epsilon over d is going to be 0.00003. And if I take this and feed it into the Moody chart, this time I get a friction factor that is approximately 0.0165. So I've gotten so this is iteration. I now have a different friction factor than what I initially assumed. So the whole idea is that I assume a friction factor, I calculate what velocity that would produce, I calculate what Reynolds number would correspond to that, and then I use that Reynolds number and my epsilon over d to calculate my new friction factor. And again, notice these are not equal. 0.02 and 0.0165 are not equal. So I'm going to go through this loop until it converges on F. So I'm going to try it again. And it should collapse relatively quickly if we're doing it right. Until we lock in and converge on an F. Okay? So this is going to become my new assumption now. And now here I'm going to work through a loop assuming that the friction factor is the previous value we calculated, which is 0.0165. F equals 0.0165. And then I'll do the same kind of thing. And again, this is where it's very beneficial to use the collapsed forms of those equations, so we don't have to multiply out the g and the d and everything every single time. We can just use a very simple equation that we can just plop a single number into. So we'll have velocity, Reynolds number, epsilon over diameter won't change, and then our new friction factor. And let's see here. So I will again say that velocity is equal to the square root of 2.48 divided by 0.0165 is equal to, so here the velocity will be 12.3 feet per second. I'll get a velocity of 12.3 feet per second. The Reynolds number I calculate will be 13,774 times the velocity of 12.3 feet per second, which will be 1.68 times 10 to the 5th, which is greater than 4,000, so it will be turbulent. That'll be turbulent. And of course, epsilon over d is still going to equal our 0.00003. Many zeros today. And this, we're lucky in this example, and that's why I chose it, and that this particular one does collapse relatively quickly. You may have some examples, or you may have some situations where things do not necessarily collapse so quickly, but this is not one of those cases. Okay? So here, the friction factor, if I actually go and take this and put it into the Moody diagram, I find that the friction factor is approximately equal to 0.0165. So we actually reached this after only 2 loops. So again, notice 0.0165 equals 0.0165. So this converges. Got it. Yay, we got it. Smiley face, everybody's happy. Anyway, so we got this, and this means that the actual velocity will be 12.3 feet per second, and the actual Q, if we wanted these, would just be V times A, which would be 0.269 cubic feet per second. So we can have our velocity and our Q here. All right, and that's a basic introduction to solving for these by iteration. And I do have another example I'd like to work through using, and this one shouldn't be too bad either, using iteration here. Okay? My second example, instead of involving a fixed length of pipe, is going to involve 2 reservoirs. Okay? So let us consider this. This is going to be a 2 reservoir problem, or a 2 tank problem, or whatever you want to call it. And so example 2. Now this is going to be, the top tank is actually going to be pressurized at a relative pressure of 20 psi, so we're going to spice things up a little bit. Welcome to engineering school, where our version of spicing things up a bit is adding a pressure to a tank. Although, who am I kidding? I recently saw a video from Georgia Tech where some students had decided to, some mechanical engineering students decided to be hilarious to create take a chainsaw engine and attach it to a tricycle, and they were built that monstrosity and were just wandering around campus on that. So anyway. So that's engineering school for you. So consider these 2 points here. This is going to be 0.1. Here's our freeboard surface here. Or, sorry, not freeboard surface, just free surface. Freeboard is something very different. That's talking about ships and things like that. And so then consider our other elevation here. So we're going to have two different tanks at different, or two different reservoirs at different elevations. And I think this actually probably would have to be a reservoir because we're talking about very, well, maybe not. Who knows? This could be any type of system. But anyway. So this difference in elevation is actually going to be fairly large. This is going to be 150 feet. So that's actually why I'm inclined to say this is more of a reservoir. But you never know. 150 feet. And our length of pipe here, the length will be 2,000 feet. So we have a 2,000 foot long, so about a little less than half a mile long piece of pipe. And a very large change in elevation, a 150 foot elevation difference. And I'm also told that I do know the flow rate. I know that this is water, I'm told that. And that the flow rate here in this pipe, Q will be 3 feet per second squared. So all this is given. And find our old friends Guyven and Find. Find the diameter, neglecting minor losses. So an example of this might be something like, well, let's say we have this could be a reservoir, it could actually be something like a water tower. Maybe the top of the water tower is pressurized by an air pump or something like that for whatever odd reason. And we need to be able to deliver water to a location, a house, 2,000 feet away, or a building, whatnot. And we know we need to be able to maintain, so this pipe is delivering water to a neighborhood 2,000 feet away, and it must be able to deliver a flow rate of 3 feet per second. And you, as a design engineer, have to figure out how big a pipe do we need. So, how big a pipe do we need? Now, obviously, bigger pipes are going to be better in the sense that they are going to have less losses. We'll see, we know how to calculate Reynolds number accordingly, all of that good stuff. But of course, the bigger the pipe, the more material you'll need, the bigger hole, the deeper the hole you're going to need to dig, all of that. So all of your costs are going to go up the deeper, the larger the pipe diameter you're looking at. So anyway, but I want to find diameter needed, ignoring minor losses. So we're going to do a very similar thing to in the previous case. So solution here. Let us first consider the energy equation. And this is going to be P1 over gamma water plus V1 squared divided by 2G plus Z1 is equal to P2 over gamma plus V2 squared divided by 2G plus Z2 plus FLV squared divided by 2GD. So let's start canceling some things out. Well, I can't cancel out the velocity, the elevations, but I can cancel out the velocities, so I'll first eliminate those. And I will say that P2 is equal to 0 because it's a free surface there, and we're talking gauge pressures. Next, I'm going to work through, again, what I'm trying to do is I am trying to develop this in terms of a simplified form. Here, I want to develop this in a bit more simplified form. So let's consider this. And so if I put in those terms, so again, I'll have kind of P1 over gamma water plus Z1 is equal to P2 over gamma. Actually, let me just go ahead and say, I'll say Z1 is 150 and Z2 is 0. So plus P2 over, actually that term is 0, sorry. That's 0 as well. I'm trying to not eliminate too many things, or not to get myself too distracted here. Times F LV squared over 2GD. So plugging in terms, 20 PSI times 144 inches squared per foot squared divided by gamma water, which is 62.4 pounds per cubic feet. And let's see here. Now, let's consider this. So we're going to end up with a very interesting equation here. This is going to be slightly disturbing, but we'll get it. Plus 150 feet equals F times 2,000 feet for our length of pipe. The velocity, now check this out. I'm going to say for the velocity, I wanted to get this in terms of diameter d. So I'm going to say V equals Q over A. V equals Q over A equals 3 feet per second divided by pi over 4 d squared. And that comes to, that V is simply equal to 3.82 divided by diameter squared. Again, I'm replacing the velocity term in the Darcy-Weishbach equation. I'm replacing it with a 3.82 over d squared, basically Q over area. And so this is going to be 3.82. Now, this is where it gets really weird because we have a velocity with a diameter squared, and we're going to end up squaring that because the velocity squared is in our equation here. So we're going to end up with a very ugly equation at the end, but that's okay. We're engineering students. We're not afraid of math. 3.82 divided by diameter squared, especially just, ordinary algebra. Divided by 2 times 32.2 feet per second squared times the diameter d. So notice I have a d squared, and then one more d in the denominator. So if you go and multiply all this mess together and solve this for diameter d, you will get the very interesting equation that d is equal to 1.18 times the friction factor to the 1/5 power. Or another way to think of it, if you prefer root notation, this is 1.18 times the 5th root of the friction factor. Isn't that lovely? But again, it's kind of ugly, but it's really not so bad. The whole idea is that I know this looks kind of ugly and kind of weird, but the basic idea is that we're trying to collapse all of our equations into something that will be very easy to iterate as we go through our loops. Because again, it's going to be a pain in the butt. It's going to be a big enough pain in the butt to multiply this out and multiply this out once. I don't want to have to do that multiple times. So I'm going to try to, you can, if you don't like solving, if you really just hate algebra that badly, you can do that. But I highly recommend doing this if you can. So next, I'm going to do the same kind of thing for our Reynolds number. So let me develop a minimized form of the Reynolds number equation. And let's consider Reynolds number. And this is going to say that the relative roughness is equal to rho water times V times D divided by mu water. That is mu W. Man, that is very confusing. Anyway, that's just the dynamic viscosity of water. So this is going to be 1.94 slugs per cubic feet times the velocity, which is 3.82 over d, which is what we had previously, divided by d, 3.82 over d, times d, and then this is going to be, 3.82 over d squared, thank you, yes. It's like the diameter should not cancel out like that. Divided by 2.34 times 10 to the negative 5, and our lovely units for viscosity that we always have, pounds second per feet squared, per square foot. And then the Reynolds number will be equal to 3.17 times 10 to the 5th divided by diameter d, where diameter d is in feet. Will be important to keep in mind as we work through this. So we have another sort of tailor-made equation, ugly but tailor-made to solve in an iterative loop. Here. So now we just do the same kind of iteration, and I'm just going to do the same thing I did before. Oh, actually, the only other thing I need to do is look at the relative roughness, which is going to be easy because this is a PVC, which we can assume to be a smooth pipe. So epsilon is equal to 0, and epsilon over d is equal to 0. And again, because this is a smooth plastic pipe. Smooth plastic pipe. Next, we're going to iterate again. Same as before. Iterate, that's a big T. Iterate. So I'm going to start by assuming the friction factor. Friction factor, again, I'm going to start by assuming my middle of the road value. Let's assume the friction factor is 0.02, something from the middle of the Moody diagram. And as you go through this, we would actually have to be very careful. Like, we would assume a friction factor, and then, however, if we went and calculated then that if we calculated the Reynolds number and found that we couldn't get we would not get that we were in the, well, I guess you could. But if say, for example, if we calculated, we assumed a friction factor, and then we calculated that we were in the laminar flow region, well, then we'd have to go back and use the equations of laminar flow, etc. But for now, let's just assume we're in the turbulent region. So diameter is going to be equal to 1.18 times 0.02 to the 1/5 power. And if that's the case, we'll have a diameter of 0.540 feet, 0.540 feet, and we'll get that the Reynolds number is equal to 3.17 times 10 to the 5th divided by the diameter of 0.540 feet, and that comes to 5.87 times 10 to the 5th for the Reynolds number, so we are in the turbulent region if this assumption is correct. And epsilon over d is 0, no problem there. So we take these two values and we get that the friction factor now is 0.0129. 0.0129. And this is not equal to 0.02, so we need to iterate some more. But as we see, this stuff does rapidly converge. So iteration number 2, and I'm going through this a bit quickly, trying to finish this example up. So let's say assume f equals 0.0129, and then the diameter d would be equal to 1.18 times, or I should say the required diameter, if we had that kind of friction factor, 0.0129 to the 1/5 power, and that will be equal to 0.494 feet. 0.494 feet, and the Reynolds number will also be fairly easy to find. Again, 3.17 times 10 to the 5th divided by 0.494 feet, and that is 6.41 times 10 to the 5th, and then again using our epsilon over d is equal to 0. This time I would get a friction factor of 0.027 or 0.0127, which in this case it actually is approximately equal to 0.0129. Now this is kind of a judgment call. So here's the issue. We know to stop iterating when our friction factor here is equal to the initially assumed friction factor. Now, you're never going to get it exactly close. I mean, yes, I mean, at least to the limits of your calculator, or you're never going to get it, well, actually, especially because the Moody diagram is a visual tool, it's limited to how many decimal places. So you're never going to get it exact, but the question is how close is close enough, and really that's a matter of engineering judgment. You'll have to use your judgment there. So, but you can still see if we went through a few more loops, we could get as close a value as we wanted to. And if you wanted to, you could actually look up the equations behind the Moody diagram, how those curves are calculated therein, and use those to get a more precise value. But anyway, then we'll just we can say that the diameter D is equal to 0.494 feet, and that would be the final result that we report, because it was asking for the required diameter therein. Or if I was actually a design engineer, if I was designing this in reality, do you know how I would solve this issue of whether it converts or not, or whether it converges or not? How close is too close, or how close is close enough? How I would solve this is just say, you know what, diameter is 0.500 feet. Problem solved. 6-inch pipe. All right, that'll do it for today. Thank you as always, and I'll see you on Wednesday. Thank you.